The next topic is electromagnetic induction and electromagnetic waves. So basically, electromagnetic induction. So this is just a continuation of electromagnetism. So we have talked about the magnetic field due to a current carrying wire in the previous topic. Now we're gonna talk about the opposite effect. And the first thing we're going to do is the Faraday's laws, Faraday's laws of electromagnetic induction, magnetic flux, Faraday's laws of induction, Lenz's law, and then if time left, electromagnetic induction. So here's the question, if current can produce magnetic field, can a magnetic field create a current? And the answer is yes. But only changing magnetic field, can produce electric current. And that was the accidental discovery of by Michael Faraday's. So that's why this is called a very famous experiment called Faraday's experiment. Faraday's discovery of electromagnetism. So he accidentally, you know, uh, discovered that something like that. So here's a simple coil, the insulated wire, right? Coil, and if you try to uh, insert the magnet in and out of the coil, you get some electrical current through the circuit. So to detect the current, of course, you'll have to you know connect it to a current meter or voltmeter, and if you insert a magnet in and out, you see some deflection due to the induced current. It's called induced current, and this whole phenomenon is called electromagnetic induction. It's a very important phenomenon. Okay, and so you can do one of these. You can either move the coil, or you can either move the magnet in and out, like that. So, what's the physics behind this induced current or induced voltage or EMF? So the physics behind that is the same thing as we did before in the previous chapter. Because a magnetic field exerts force, on moving charge, and that's the main physics behind that. So, to explain this induced current in electromagnetic induction, let's take a simple case with just a metal bar. This is just a metal bar, right? And so you move it in magnetic. So in this example, this is the magnetic field. The magnetic field is into the pills, right? And you move this metal plate, say in this direction with some velocity. And as you know, metal has so many electrons, right? As a free charge, electrons. And when you move it in magnetic field, the magnetic field exerts force on that electron, right? And it moves. So based on the rule, actually, right hand curl rule, you can see the electrons move this way, and the positive charges move that way. And at some point, the magnetic field and electrical field, which is generated by the separated polarized charge, will balance, and then you get the polarized charge distribution, and that's the main cause of electromagnetic induction. That's the main cause of electromagnetic induction. It's because magnetic field exerts force on moving charge. So, how much voltage you get actually on a plate is given by this formula. So delta V is, which is the potential difference, is electric field times length, and delta V is EBL sine theta, right? So V is the velocity, B is the magnetic field, L is the length, and the sine theta is the angle between the velocity and the magnetic field. So this is called motional EMF, induced EMF, motional EMF, and this is because of the charge separation, you know. So here's an example of some example of induction, induced EMF. So in 1996, space shuttle deployed a satellite at the end of 20-kilometer long conducting tether, and since Earth has its own magnetic field, and this satellite is actually moving across, was sweeping the Earth magnetic field, a potential difference of up to 3500 volt, 3500 volt was induced, developed between the shuttle and the satellites, in Earth, due to Earth magnetic field. Okay. So, and voltage induction, so when same thing actually, when airplanes move, when airplanes fly, um, there is a chance that there is some induced voltage develop across at the end of the wing, airplane wing, because this airplane wing is aluminum metal and is moving across Earth's magnetic field. And so let's say the airplane is moving north, and this is the magnetic field, Earth's magnetic field, right? The component which is perpendicular to the plane, and because of that, it induces some charge, and based on the rule, positive charges will be this way and negative charge will, and that creates the potential difference of voltage, and you have to be very careful in these things. So induced current. So what's the, so once you have the induced voltage, you can calculate the induced current easily. Induced current, right, it will be just using ohms delta VOA over. But this is the induced voltage in a bar, in a metal bar or metal plate, motional EMF, right? That much voltage will be induced, VLB, and then you can do this, and then this is the power dissipation. Power dissipation is just, uh, you know, power dissipation is just I square R, where I is this, right? And this will be the power dissipation in a rod when you move in a magnetic field. Okay. So next, so this is how the credit card machine, reader, reads your car information. So because when you swipe your credit card, I mean the old style magnetic credit card. When you swipe a card, actually, it induces tiny electrical voltages, electrical energy, in your card reader, and the card reader will read the data. It's just the electromagnetic induction. So here's some examples. So you can clearly see. So just a conceptual one. A square conductor moves through a uniform magnetic field. The magnetic field here is out of the page, right? Which of the figures show the correct charge distribution on the conductor? So you just use the right hand, you know, remember from our previous chapter, right hand um, call rule, right? So first you have to point your fingers towards the velocity, which is up, and you have to curl your fingers towards the magnetic field, which is out of the page. So then the positive charges will move towards the thumb, right? So thumb, right? So the force is given by thumb is that way. So this is the right picture. The positive charges will be to the right, and obviously negative charge will move to the opposite side. So this is E is the right answer for that. So, and there are many applications of electromagnetic induction, So electric generators. So electric generators are opposite effect of, electric motor. So electric generators is basically, it's a coil, rectangular coil, right? And it's connected to the outer circuit like that, with a brush, carbon brush. And when you rotate that coil in a magnetic field, it induces current, right, as shown. And then you get the electrical output. So in this example, it's a AC output, alternating current. It's not direct current like battery because the direction of the current changes alternately. So this is an example of electrical generator. So the next is magnetic flux. So what is magnetic flux? So magnetic flux is simply the collection of the magnetic lines of force, magnetic lines, magnetic field lines, collected over the given area. That's called magnetic flux, right? So if the coil is, so here's an example. This is the side view. This is the side view of, so this is say a rectangular coil. The magnetic field is going that way, right? And this is the top view. Same thing, but with the top view. Now, what happens if you tip, right? If you rotate the coil with some angle theta, now fewer number of flux will pass through the, fewer number of lines, magnetic lines or magnetic flux will pass through the coil, right? The effective area will decrease, right? here it has the maximum flux. It has the maximum flux, right? Magnetic passing through the coil, but when you rotate it by some angle theta, so the effective area will be reduced. So by how much? So by cos theta. So then the flux is defined by the effective area times the magnetic field. So the product of the effective area of the coil, right, times the magnetic field is defined as the flux, the magnetic flux. And the effective area is, AB cos theta. The effect because this component, the area vector, right, is component on the magnetic field is A cos theta. So this is the general formula for magnetic flux. AB cos theta. A is the area of the coil and B is the magnetic field, and cos theta. Theta is the angle between, the area of the coil, which is given by the normal to the coil, right, with the magnetic field. And the unit of flux, magnetic flux, is wavers. Okay, it's measured in wavers. It's from name of the scientist. So here's another same thing to explain here. The most important law in electromagnetic induction is Faraday's laws of electromagnetic induction, and it's basically calculates the induced voltage in a coil due to induction. And this is the statement of Faraday's law. Actually, it's Michael Faraday's laws of electromagnetic induction. It simply says the induced EMF, which is the voltage in a loop, right, or in any coil, is induced only when the magnetic flux through the loop changes with time, and the magnitude, right, the magnitude of the voltage induced, EMF induced E, is given by this formula. Okay, negative N delta phi over delta T. Okay, and negative sign I will explain in the next slide. N is the number of turns in the coil, and delta phi over delta T is the rate of change of flux. So it basically says the magnitude of the induced EMF in any coil is proportional to the rate of change of magnetic flux, and we just defined magnetic flux in the previous slide, right? So basically this is the formula actually. So N is the number of turns, and flux is basically area times AB cos theta, right? And N is the number of turns. So basically, and negative sign has to do with some other law called Lenz's law, which we will explain next slide. Okay. So the next is Lenz's law. It's a very important law in electromagnetic induction. So let me first state the Lenz's law. Lenz's law says there is an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. And the direction of the induced current is such that the induced magnetic field always opposes the changing flux. So basically, Lenz's law gives the direction of the induced current. You know, so what it basically says is that so when you try to induce current by inserting a magnet, through a coil, something like that, you always feel an opposition. Okay, that's what Lenz's law say. So if you try to insert a magnet into the coil, you feel a repulsion, from the coil, because it will induce a current in such a way that the induced magnetic field in this coil will try to repel the incoming magnet. The same thing, if you try to pull the magnet out, then you feel attraction. So that you always feel some opposing force, and this animation and this GIF animation explains that. So if you try to insert a magnetic north, right, so the coil induces current so that it develops a north pole this side, right, and so that it feels opposite. So when you try to insert a magnet, the magnet feels force or repulsion, but when you try to pull it apart, pull it away, it feels attraction. So it's always opposing, and that is necessary because then because of this opposing force, you will have to provide some work against that opposing force, and that work is actually converted. That work done is converted to the electrical energy. So Lenz's law simply says is nothing is the just the consequences of the conservation of energy. So it's basically your work done is basically converting into electrical energy. That's what is happening. And without opposing force, it's not possible. Otherwise, you will be producing electrical energy, without out of nothing, and that violates the principle of conservation of energy. Okay. So Lenz's law is the direct consequences of conservation of energy. It's nothing new. So here's the golden rules for applying Lenz's law in solving the problems. So the first is uh, first, if you are trying if you insert a magnet into a coil, say, so the flux will increase, right? So increasing flux. If the flux is increasing, the induced magnetic field, right, points opposite to the applied field. If the incoming flux is increasing, while example is when you try to insert a magnet into a coil, the flux is increasing, right? Then it will induce current in such a way that the induced magnetic field will oppose. So, and the next is decreasing field, right? If the flux through the coil is decreasing, the induced magnetic field um, points in the same direction. Okay, and steady flux. If the flux through the coil is not changing, steady flux, so there will be no induced magnetic field. Okay, so these are the golden rules. And here's the explanation. If you try to insert a magnetic north, right, so it will induce, right, the coil will induce a current so that it will oppose. So this is the B of induce, right, and this is the magnetic field due to this magnet, right? So see how they are opposing. So that's why then you can definitely say the coil has counterclockwise current, because counterclockwise means upward current, right? So same thing. If you try to pull the magnet away from the coil, now based on Lenz's law, the it will induce the electrical current so that it has to now attract, right, because it has to always oppose, so it has to be in the same direction, say B induced and B are in the same direction, right, when you're trying to pull the magnet away from the coil. So you have now clockwise current because the induced field is downward means clockwise, right? So that's how you figure out the induced current direction. So here are some other examples of this induction. So you will see this induction oven uses the same principle of magnetic friction. You can call it this magnetic friction because it uses alternating current to produce alternating magnetic field, and the alternating magnetic field will actually induce this eddy currents. It's eddy current, and because of magnetic friction, it's a contactless generation of heat. And here's other good example is that if you drop a powerful magnet, so this is a near beam magnet. If you drop a powerful magnet through a copper loop, something like that, copper tube, it has significantly slows down. You can clearly see it has significantly slows down, and it's because when you try to drop, right, it induces current in the copper loop, right, copper tube, so that it will always oppose the incoming flux. So here's an explanation. Here's the explanation. Okay, and it is a direct consequences of the Lenz's law. So the incoming induced current will always oppose. It's called something we can call something we can call magnetic friction. Magnetic friction. So this the induced current here, which will oppose, right, the incoming flux, is also called eddy current. Okay. So here's now some a few questions. So here's you have a long straight wire. It's carrying current I, right? And because of that, it produces magnetic field. These are the magnetic fields due to the wire, right, in this side. Now you have this loop of rectangular coil, right? Is pushed towards the wire. So it's acting. What current do you get? Clockwise or counterclockwise current do you get? So let's first try to understand. So first of all, the magnetic field, we first you need to figure out the magnetic field due to the wire in this region. So into the page, right? So and magnetic field is into the page, and since this coil is moving uh, towards the coil, the flux is increasing, right? Flux is increasing. Flux, the magnetic flux through the coil is increasing because why? Is going towards the stronger and stronger field produced by the wire. So that's why Lenz's law said if the flux is increasing, right, the induced current has to oppose it. So it will produce the induced current so that this induced field has will oppose it. Oppose means since the external field is this is you can say external magnetic field is into the page. Now it will produce this coil will produce induced field so that it will produce in opposite direction. Opposite means like this. So this is the induced, and this is the super important thing to understand, right? The induced field will have to oppose the external field, and oppose means it has to be at the center. It has to be out of the page. So to produce out of the page, you need counterclockwise current. So this is the direction of the induced current. This is the direction of the induced current in the loop. So you get in this example, you get counterclockwise current in the loop. And similarly, if you try to uh, uh, push this away from the wire, of course you will get clockwise current. So here's another example. A bar magnet is pushed towards a loop of wire as shown. Which of the following is true? The loop now has loop has counterclockwise induced current, clockwise, counterclockwise or no current. So it's the same explanation. Since you are pushing this magnetic north towards the coil, so this is the external field, right? This is the external field you can draw. This is the external field, right? This is the magnetic flux, right? Due to the uh, pole, right? And now, since from Lenz's law, since you are pushing this magnet towards the loop, so flux is increasing, right? Flux through the loop is increasing order. So from Lenz's law, if the flux is increasing, it will induce current so that it will oppose. So it has to now oppose, right? This has to the this is the magnetic field induced by the loop. This is the B induced. It has to oppose. And to produce a downward current, you need a clockwise current. Okay. So answer is clockwise. You get clockwise current in this. Okay. So just try again. And the same examples, there are many examples. So let me show you one example here. So one more example, similar example. So you have there are two loops, two circle loop. So the upper circle loop is connected to the battery, right? Battery. This is the positive side. This is the negative side, and this is the switch. This is the switch, right? And another circular loop is placed pretty close to the top one, right? And it says when you turn the switch on, what current and that moment of time, right? When you turn the switch on, what current do you get in the this nearest loop, this one? So what current do you get? Clockwise or counterclockwise, right? And let's figure that out. First, you need to figure out once you turn the switch on, right? The current is in increasing order in this direction, right? So this is a counterclockwise current, right? And it's increasing. So its magnetic field will be something like that, right? This is the magnetic field through the downward is in upward direction. Now, from Lenz's law, right? If the flux is increasing, and because you're turning the switch on flux at that fraction of second, the flux is increasing. You can say the external, right? Now this has to induce a current so that it will oppose, right? So here's the induced current, induced field. Induced field has to be opposite to the external field. So the induced field has to be downward. Downward means clockwise current. Okay. So again, answer is clockwise current. And here's the explanation. I try to explain in this making this GIF animation. So try to understand this figure. So when you turn the switch on, right, you get clockwise current in the bottom loop. Okay. Now opposite will happen. If you try to turn the switch off, right? If you try to turn the switch off, opposite will happen, right? So try to figure out this diagrams, the field diagrams. Now you get counterclockwise current, obviously, right? So try to understand this animation.